Okay, so welcome everyone to today's lecture. This is the 10th lecture of the course on Cyber Physical System Fundamentals, a course in which I'm teaching Embedded Systems Fundamentals of Cyber Physical System Design. Today's lecture is corresponding to some of the material of the third chapter in the companion textbook. More specifically, this is the second lecture corresponding to that third chapter in the companion textbook. That third chapter is entitled Embedded System Hardware. You might remember from the last lecture that the different topics that I'm covering in this chapter are structured according to their position in the so-called hardware in a loop. In this hardware in a loop, we are starting with the physical environment. For that reason, we are also calling these systems cyber physical systems. And then we are continuing with sensors. Then we have discretization, both in values and in time. Then we have information processing. Potentially, we also have a display. We have the conversion back to the analog domain. And then we have actuators, and we have a potential impact of these actuators there on the physical environment. So today, I will talk about information processing in embedded and cyber physical system hardware. With respect to embedded system hardware, we do have requirements that are carried over from the general set of requirements for embedded and cyber physical systems, and therefore I have included one slide that I did already show in the very first lecture. In the very first lecture, I stressed the fact that embedded and cyber physical systems have a number of properties, including the fact that they must be efficient. And efficiency comes in a number of flavors. These flavors include the fact that they must be code size efficient, runtime efficient, weight, cost, and energy efficient. Now for today's lecture, for the context of processing, I do care less about cost and weight efficiency, but I do care about code size, runtime, and energy efficiency. And I will discuss these three flavors of efficiency in today's lecture. And I'm going to start with energy efficiency. Now, with respect to energy efficiency, I have observed that there is currently some confusion, because there are so many different reasons why we are caring about energy efficiency that sometimes people start to mix up the different reasons, and therefore I'd like to have a clarification in this context. So for what reasons are we interested in energy efficiency? Well, there's a couple of reasons, including global warming. We know that global warming is a problem, including the cost of energy, including the increasing performance, which requires also an increased amount of energy. And resulting from the increased amount of energy, we do have problems with cooling. We have to consider the thermal effects. We have to avoid hotspots on our systems. And linked to the fact that we have an increased energy consumption, we also have the problem that we have high currents, especially if these device dimensions are getting smaller and smaller. Current densities might be getting very large, and therefore we can also have an effect called the metal migration, which means that the metal starts to flow like a pudding, which is something that you don't expect from a solid-state device. And also linked to that, we have problems with reliability. It might happen that future systems wear out over time, and that's something that we would like to avoid as much as possible as well. And then people care about energy efficiency because in certain cases energy is a really scarce resource, so we really have to design our system with a very, very small amount of energy being available. Now, whether or not these reasons apply really depends on the context in which we are using information processing. And there are several contexts, and more in particular, there are several different environments in which we have more or less power available. We can use information processing in a plugged context, which means that we have main power supply available. We can use them in a way where sometimes we have a connection to the main power, and sometimes we have to live from the batteries. And then there are contexts where we hardly ever have a connection to some power outlet, and therefore we have to live with the power or energy that's available there. And we can see that global warming and the cost of energy are mainly important only for the plugged systems. Because these other systems, they can carry around with them only a very small amount of energy, and therefore the overall impact in terms of the global warming of these more mobile devices is rather small, even if we have quite a number of them. And then on the other hand, energy isn't really a scarce resource if we have a plugged system, because there the designers are really exploiting the fact that we have a connection to main power, and therefore energy isn't really a very scarce resource there. It may still be a resource to be considered, because even from a power outlet there's a limited number of, there's a limited power that's available, but still it's not really a scarce resource. So that's, I think, a clarification that was needed, because otherwise people are confusing the different reasons. Sometimes people argue that global warming is also an issue for the energy that you burn in a mobile phone, which from my point of view is not, because there are orders of magnitude between the energy that you burn in a server, in a computer center, and the energy that you burn in a smartphone. So if you look at this slide, we do already see that sometimes I refer to energy efficiency and sometimes I refer to power efficiency. So this might again be a source of confusion. So should we really care about energy consumption, or should we care about power consumption? Well, first of all, I think you know that the two are very closely related. Energy is just the integral of power over time, so they are very closely related. And graphically, we can demonstrate this by pointing to the fact that energy corresponds to the area underneath this function, the function describing the consumption of power over time. So we see both are very closely related, but they are still different. This means whenever I would like to optimize the energy, I should really use energy as a cost function. And whenever I really want to optimize the power efficiency, I should really use power as the cost function. Now, should we care about the energy consumption, or should we care about the power consumption? What's actually more important? And on this slide, I have put a number of reasons why we should potentially care about the power consumption and why potentially we should care about the energy consumption. There are some reasons why we should care about the power consumption. So, for example, the design of the power supply and the voltage regulators. For this design, it's very important that we try to minimize the the power consumption. And also, if we look at the short-term interconnect, the dimensioning of interconnect and short-term cooling, it's also important that we look at the power consumption. On the other hand, there are also reasons why we should look at the energy consumption. In many cases, there is only a very small amount of energy available, especially if we have mobile devices. We have to carry the energy around with us using batteries, and we know that battery technology is improving only very slowly, and therefore we really have to care about the energy consumption, especially for mobile systems. And then cooling may also be important, because sometimes cooling is very expensive. You might know that sometimes a fan for a high performance microprocessor can cost more than the processor itself. And in certain cases, there is only a very limited space available. So, for example, in your very thin mobile phone, there would hardly be the space to put a fan there. So therefore, that's clearly an example where not enough space is available for some active cooling, like cooling from a fan. Then we have thermal effects. These devices are getting too hot if we burn too much energy. And linked to that, we have issues of dependability and the lifetimes that we are expecting. So we see that in general, we have to take both into account. Sometimes one requirement is dominating over the other, and in other cases the other requirement is dominating over the first. So it really depends on the context. There is no general rule which of the two is more important. So next I'd like to point out that there are a number of contexts in which the energy or power consumption is really a problem. And one of these contexts is the fact that we have a increasing power density, and in this case I'm referring to processors like you use them in a PC. There, over time, we can observe that the power density in terms of the number of watts that are burned per square centimeters has increased. I don't call this improved, it has increased. And we see that this followed more or less a straight line. Then for a certain generation of processors, there was a certain deviation from the straight line, but still the energy density is pretty high, or the power density is very high. And we see that we are almost approaching there the power density of the nuclear power plant, which is a very high power density. Fortunately, we haven't reached the power density of rocket nozzles or the sun surface so far. Yeah? But nevertheless, we have left and surpassed already the power density of hot plates in the kitchen. Now, one idea could be that we consider this as an advantage that we could take into account and actually exploit this situation. So how can we exploit the fact that the power density on a processor is exceeding the power density on a hot kitchen plate? Well, of course, we can try to prepare our meals that way. This is, for example, what we could try to do. And it was demonstrated in Taiwan that indeed it is possible to fry an egg there on the processor. Just to play safe, I don't recommend to try to repeat this, because that may be the last time that you have used your processor. Yeah? But the person who did this experiment, he confirmed that he later ate the egg, and he said that it actually tasted lovely. But this little demonstration also allows me to remind you of one fact. Because, strictly speaking, we are using a wrong wording in this context. We are frequently talking about energy consumption. Now, we know from physics that energy is, strictly speaking, never consumed. There is the conservation of energy, and we are just converting energy from one form into some other. And in this case, we are converting energy from its electrical form into thermal energy. So therefore, strictly speaking, when we talk about energy consumption, this is wrong. We are just generating heat. Now, next, I'd like to point to another instance where we see the problems that are popping up. And in this case, I'm referring to the increasing performance requirements for mobile phones. We can look at the workload in terms of the number of operations that are required per second. And we see that from one generation of mobile phones to the next generation of mobile phones, measured in multiples of 5 years, we see a tenfold increase in the number of operations that are required. So we see that computational requirements are increasing at an extremely rapid rate, at an exponential rate. And unfortunately, this also means that for a fixed silicon technology, we will necessarily burn an additional amount of energy. Fortunately, silicon technology is also improving, but we might reach an end there. There are actually many more instances of the power energy problem. We have metal migration, we have problems with cooling, we have problems with limited supply of energy, etc. So therefore, it has been found that the limited availability of energy is one of the most important constraints for the design of cyber-physical and embedded systems. And it has also been observed that the same effect becomes more and more important also for the server business and for standard PCs. So therefore, we would like to contribute to considering that problem and possibly trying to help to solve that problem at least a little bit. Before we do this, we have to watch carefully where the power is actually consumed, because we would like not to optimize in an area which overall is not that important. When we look at a mobile phone as an example, in this case, we might have the impression that a lot of the energy is spent anyhow on the display, on the RF part, maybe on the audio part, and that processing is not that important. However, as you can see from this pie chart, you see that indeed the RF part, the audio part, they are consuming a significant part of the energy. However, the application processor in combination with the memories are also having their share in the overall energy consumption. So that means it's not just I/O which is consuming the energy, it's also the processing. And we do have to care about the processing as well. Looking a little closer at processing, we can observe that there are also all kinds of processing that are going on in, for example, a smartphone are actually relevant. From this pie chart, you see that the graphics is in charge of a major share of the power consumption. Media processing, that means processing of audio and video. The RF part is indeed in charge of a major share of the energy consumption, and the application processor is also having its share. So that means, as a conclusion, we do have to consider all the different components here. It's not that we can argue, well, this part of our system is hardly relevant for the overall energy consumption. We have to look at all the different components here. When we try to analyze the areas where we are consuming the power a little further, we have to introduce one important distinction which is really needed when you look at the energy consumption. And this is the distinction between the static and the dynamic power consumption. First of all, let me explain the dynamic power consumption. The dynamic power consumption is caused by charging capacitors that come with any integrated circuit. We cannot really avoid these capacitors. They are fabricated as part of the fabrication process. They are fabricated as part of the layout of the different transistors and wires. So we have these capacitors there. And this means that whenever we have, for example, a standard output somewhere in our circuit, we have to charge and discharge these capacitors. Now, for the power that we are burning there, on average, there is one well-known equation. And according to that equation, the average power which is burned there due to charging and discharging the capacitor depends on the capacitance of that capacitor. And it also depends on the supply voltage. It depends on the supply voltage quadratically, and also on the frequency. That means the higher the clock frequency, the more power we burn there. And then we have one factor alpha, which reflects the switching activity, which reflects how often we actually switch per clock period. As we can see from this equation, there is this very important dependence on the supply voltage, which is a quadratic dependence. So if we were able to reduce the supply voltage, we would also be able to reduce the power quadratically. So we will see that this is very important for energy minimization. And then in addition, we have to look at the so-called static power consumption, which is a power consumption that takes place even if we don't apply any clock signal. And this happens because there is a certain current which is flowing through this path from VDD to ground, even if we are not charging this capacitor. And we know from the people who are working on the semiconductor technology that the contribution of the static power consumption is increasing when we work with smaller and smaller device dimensions. So therefore we know that this leakage is becoming more and more important as we move towards smaller devices. So now that I have introduced these two terms, we can look at the predicted future of, for example, consumer portable systems. So that means kind of smartphones. And there we see that it is predicted that in the future all the four contributions which are mentioned down here are relevant. So we see that static and dynamic memory and logic power consumption are indeed important, and that again we cannot neglect any of the four. We have to look at all four of them. Also from this diagram, which is based on this International Technology Roadmap for Semiconductors, or ITRS roadmap, we see that there is a certain problem, which is again pointing to the fact that we have a problem with the power consumption. We know that for a mobile phone, we should not burn more than some power between 0.5 and 1 watt, because otherwise we have two problems. One problem being the fact that we just have a too short battery lifetime, and the other problem is that this device would get too hot, so that we would burn our fingers when we use a mobile phone. So therefore, we should stay below this blue line over here. But this extrapolation from today's technology clearly shows us that right now there is no means whatsoever to stay below the blue line. So some new tricks, some new ideas are really needed to avoid fans in smartphones. Yeah, and I think users would not like to have fans in smartphones. Okay, so we see that there are some problems here. Okay, so therefore I'd like to start the discussion of some techniques for reducing the energy consumption, and I'd like to start with the so-called dynamic voltage scaling, which exploits this quadratic dependence of the consumed energy as a function of the supply voltage. So I'm just repeating that equation over here that we have already seen. So we know that if we don't take leakage into account, we can reduce the power consumption quadratically if we reduce the supply voltage. However, decreasing the supply voltage has a negative impact on the frequency that we can apply to a CMOS device, or phrased in a different way, it has an impact on the delay of the circuits. So this is an equation which describes the delay of CMOS circuits, and we see that there is a certain dependence on the supply voltage. Now, for the time being, for the sake of simplicity, I'm assuming that we can exploit the fact that the so-called threshold voltage is, in some cases, at least small compared to the supply voltage. This difference is getting smaller and smaller, but for the sake of simplicity, I'm assuming that we can ignore these threshold voltage there. If we do that, we can simplify this equation, and we would have, as a result, one equation where we see that the delay is inversely proportional to the supply voltage, which means that if we decrease the supply voltage, we will be decreasing the power quadratically, while the runtime is increasing only linearly. And this is a very nice effect that we can try to exploit. There is a standard chain of arguments that we can use for explaining how we can exploit these facts. And this chain of arguments will tell us that, in general, it's very good to use more parallel operations that are performed by a circuit which is relatively slow, than to perform only one operation at a time, which is performed at a very fast rate. So the standard chain of arguments is as follows. We start with the equation reflecting the dependence of the power on the voltage. We also start with the equation that tells us that the clock frequency that we can use depends linearly on the supply voltage. Then we assume that initially we are executing an application, we are executing a program, only one operation at a time. And for this we need a certain energy which is computed as the power, which in this case is assumed to be constant, times the runtime that is required for that application. And I'm assuming that we want to fix this runtime to a certain value. Then furthermore, we assume that the runtime is inversely proportional to the frequency. That again is a simplification. It doesn't consider the fact that the supply voltage might have a different impact on the different parts of our system. Now the next step in this chain of arguments is that we move towards parallel execution. And we assume that we are executing better operations at a time. So we might be executing better operations per clock step. Since we now have parallelism, we can afford to spend more time on each of these operations, which means that we reduce the clock frequency by a factor of beta. Now, since we reduce the clock frequency, we can also reduce the voltage, and we reduce it also by a factor of beta. As a result, we would be reducing the power consumed in such an operation by beta squared. Since we are now executing beta operations per clock, we arrive at a new power consumption, P prime, which is beta times the power consumption per operation. And this means that the new power consumption is the old power consumption divided by beta. So we reduce the power consumption. We assume that we still have the same execution time. T prime is equal to T because we are executing still overall the same number of operations. And the energy that we are burning there is equal to the new power times the execution time, which is the old execution time. And that means the new energy is the old energy divided by beta. Now I have to admit that in this chain of arguments we used a couple of approximations. But nevertheless, the trend is correct. The trend clearly tells us that it is better to execute more operations in parallel and to execute each of these operations at a rather low speed than to execute only one operation at a time but do this at a very high speed. And this is the standard chain of arguments which is applied in many cases. So it is the key reason, for example, for this trend to using multi-cores in PCs, because we could build processes that could execute only one operation per execution time at a time. But such a processor would be extremely power hungry and it would be close to impossible to cool it. Yeah? So we have seen that this dynamic voltage scaling is one way of reducing the energy consumption. We also have to look at the different platforms that are available to us. And in this case, I'm repeating one chart that I have already shown earlier. In this chart, we see the energy efficiency in terms of the number of operations that we perform per unit of energy, that's per joule. And we see that for some processes we have a lower energy efficiency and for others we have a higher efficiency. And we see over here that for ASICs, for application-specific integrated circuits, we obviously have the highest energy efficiency. So therefore, we might like to look first at these ASICs because they promise the best energy efficiency. So let's look at ASICs. Well, with ASICs, there is a very important problem, or there are maybe even several problems. Because designing application-specific circuits comes with a couple of disadvantages. First of all, it takes a long time to design these circuits. They are very complex, and you need possibly thousands of designers to just design one of these circuits, so that's a huge effort. Also, there is a lack of flexibility. If there is an error in the circuit, you might have to do the next circuit, you might have to do the next fabrication, and that is a very costly and time-consuming process, and therefore you try to avoid it. Also, this approach is a very expensive approach because you need this huge set of designers, and we know that just fabricating the masks that are needed for fabricating finally the circuit are extremely expensive, and therefore you try to avoid it. So there are only a limited number of cases where we would like to have our own application-specific circuit. If we go for ultimate speed, we possibly cannot avoid it. If ultimate energy efficiency is a goal, we possibly cannot avoid it. And if very large numbers are sold, then maybe economically it's feasible to spend the money on the design of these circuits. However, we see that the areas in which we can use application-specific circuits are becoming smaller and smaller, and therefore in this course we are not considering hardware synthesis. We are just looking at processes, and we will also look at FPGAs, but in this course we will not look at ASICs anymore. So therefore, let's look at processors. Well, with respect to processors, we see that in this diagram we have several kinds of processors. We have digital signal processors, we have microprocessor units, we have RISC processors. So we see in this diagram we have a number of these processors included, and there may be the question, well, if we are going for the flexibility which is offered by these processors, if we would like to exploit the programmability of these processors, then how far can we go into this corner of the diagram? I'm calling this corner of the diagram the sweet spot. That's where we would like to be. There are some examples that clearly demonstrate that it is feasible to get very close to the maximum that we could achieve with ASICs. So for example, there is this special processor that was designed at Infineon. It was designed for a special purpose. There are so-called overtaking assistants which are integrated into smart cars that try to help the driver to avoid any collisions while overtaking. And obviously you need very high performance processors there to be integrated into the mirrors because otherwise you cannot really analyze if it's safe to overtake or not. In this case, we have a chip which includes several processors. We have a DSP processor there. We have application-specific processors that are especially designed for that purpose. And we can look at the power consumption there. It's 3/4 of a watt. And we can see how many operations we can perform per second. And depending on whether we have 8-bit or 32-bit operations, we will be in different areas here, but we will still be in the kind of sweet spot area there. So we are actually getting pretty close to the energy efficiency of application-specific circuits, but we still have programmability. And there is a second case which also demonstrates that we can get pretty close to that energy efficiency of ASICs. There is a processor that was designed by NXP in the Netherlands, and in this case we have a chip including a couple of specialized processors. You see there is one MIPS processor, two trimedia processors, and quite a number of co-processors, many of which are specialized. And doing the calculations again, we will find that we are getting very close to the energy efficiency of ASICs there. So again, we have a case which demonstrates that it is feasible to get close to the energy efficiency of ASICs and still maintain programmability. However, we have to accept that for these chips, we have so-called heterogeneous components. That means we don't have components of the same type, but we have components that are optimized, say, for GSM telephony. We have components that are optimized for the built-in digital camera. We might have special processors that are doing the encryption. And if we have a certain use case, for example, a 3G telephony going on, then only some of these optimized processes will be turned on and others will be turned off. You can see this in this little table where for this use case we see that some of the components are turned on, some are only conditionally turned on, and other components are actually turned off. These are indicated in this diagram by this black color. That means for that particular use case, that part of the chip is not powered, which leads to a very interesting buzzword that you find even in economic newspapers these days. The buzzword is dark silicon. Dark silicon means that we will possibly not be able to provide all the parts of a chip with power at the same time. And we are seeing this already in this particular case. But this becomes even more drastic in other cases. And for this slide, I'm moving towards servers. So we are leaving embedded systems for the time being and looking at servers and looking at the processor chips that we are using in servers. There I'm using a slide by a colleague from EPFL. And that colleague has looked at the future of chips that we are using for servers. It was predicted that in the future for the so-called 22 nanometer technology, the optimal area for the chips will be 110 square millimeters. So that's where we have a good balance between the effort that comes with the fabrication and the resulting yield. And also it was predicted again by the ITRS roadmap, that the power that would be used for these chips would be 130 watts. Beyond the 130 watts, cooling becomes rather complicated, so we try to avoid that. So given the chip area and giving the power requirements, we can look at the constraints that we have. So first of all, if we just consider the chip area, we can span the chip area either for lots of processes that have very small caches, or we can have a smaller amount of processes that have a lot of caches. And this so-called mustard line corresponds to the trade-offs there. But if we look at the power constraints, we see that we are much more constrained actually. If we would apply the maximum clock frequency that is predicted for these processes, we would be constrained by this black line down here, which means that for systems having only small caches, we can power up only 10 to 12 processors, even though there may be about 200 processors on the chip. So that means only about 5% of the cores on such a chip could be powered on at the same time because we are power constrained. And that is really what we call dark silicon. It means that 95% of the silicon are not powered and only 5% of the silicon are powered. That's what we call black silicon. Now, in order to get around that really stupid design, we try to exploit dynamic voltage scaling again. And we try to exploit the fact that by decreasing the voltage by a factor of 2, we can reduce the consumed power by a factor of 4. And we can do this for a couple of chips. So for example, this is a slide that I borrowed from Intel, which tells us that by reducing the voltage, we can indeed reduce the power consumption. So for these X-scale processors, we see that if we reduce the voltage from 1.8 volts to 0.75 volts, we are able to reduce the power consumption significantly, while maintaining still a reasonable performance of the chips. So that means that for these commercial processes, it has already been demonstrated how we can reduce the power consumption by voltage scaling. We can apply the same technique to these future chips, where we can try to provide more of the cores with power. And looking at these other colors, we can see that indeed by using a reduced voltage, we can power on more of these cores while still respecting that 130 watts power constraint. So if we use just 9 gigahertz, we can power on up to 16 processors, and if we use lower and lower voltages, we can power more and more of these processes. In this case, we still have used one simplifying assumption there. We haven't considered the bandwidth. If we would also consider the bandwidth that's required for these architectures, we would find that not all these designs are actually reasonable, and we would find that considering the I/O bandwidth, the optimum design would be somewhere around there, close to 44 processors. But that also means that even with voltage scaling, we cannot use more than 44 processors in a chip that might have 200. Yeah? So we would be using 25% of the processors instead of just 5%. It's better, but still something to think about. Now, currently I'm talking about techniques for reducing the power consumption for processing. One technique that is available with most of today's processors is dynamic power management. With dynamic power management, we are exploiting the fact that we need the full power only if the processors are in full operational mode. However, if there is nothing to be done, then we can use less power. So that is, for example, possible with the strong ARM processor, where we can put the processor into so-called idle mode, where the processor is waiting for some software routine to wake up the processor again. And this is feasible if the processor is consuming only 50 milliwatts instead of the initially 400. And we can go even further. If we turn off the power applied to the processor completely and keep the power available only in some external power regulator, in that way we can reduce the power consumption to just 160 milliwatts. However, when we want to restart the processor, we have to restart the entire setup routine again, because the processor has forgotten all the different content there of the registers there. So therefore, it takes quite some time until we are back to this run mode. So that's a trade-off, of course, and we have to figure out when we should be having that transition that brings us into the sleep mode, because 160 milliseconds is something which the user can already notice. And if that happens too frequently, the user could be bored by the delay. So that's something that we should avoid whenever feasible. So that concluded the discussion of some of the techniques that can be used for reducing the energy and power consumption in processing. There are actually many more techniques that are available. It's impossible to provide a full overview there. Because in the last 10 to 15 years, low power design has been one of the hot topics at conferences. So therefore, you will find not just hundreds, but maybe thousands of papers that deal with techniques for reducing the energy and power consumption.